Hello and welcome back to Hilbert Spaces, the video series where we talk about functional analysis in inner product spaces. And indeed, in today's part 16, we will finally talk about operators, so-called orthogonal projections. These are special operators defined on a Hilbert space. However, before we start with the definition, I first want to thank all the nice people who support this channel on Steady, here on YouTube or via other means. And please don't forget, with a Steady membership you have a lot of advantages and you can find them with the link in the description. So with that out of the way, we can immediately start with the general setting of this video. Namely, for everything we do now, we assume that we have a complete inner product space, so a Hilbert space X. This is important because we can use that we always have an O and B of X, and we can use our orthogonal projection decomposition for every vector in X. And we can already demonstrate that with the following proposition. There we will consider a closed subspace U in X. And indeed, we already know that the orthogonal complement in the Hilbert space is always a closed subspace. So this U perp is a closed subspace in X, and now we can form our orthogonal complement again. And in fact, if we do that 2 times in a row, we get our original U out. So maybe this property does not surprise you so much, but we should definitely write down a proof of it. And since we have to show a set equality here, we can just show 2 inclusions. And the first one is quite simple. If you take any vector U from the closed subspace U, then you can combine it in the inner product with any X from our orthogonal complement. And of course, such an X can only be in the orthogonal complement of U if it vanishes in the inner product with every U from U. In other words, we definitely know that we have 0 for this inner product here. However, since we have it for every X here, we know that U, by definition, lies in the orthogonal complement of the orthogonal complement, which is exactly our first set inclusion here. And now the next one is a little bit more work, but fortunately we can already use a lot from former videos. In particular, we know that we have the orthogonal projection, so we can decompose every vector y in X. And of course, for our starting point here, y is chosen from the double orthogonal complement. But also this y has a unique decomposition if we want to project it onto our subspace U. So in short, we can just say that y is equal to p plus n. And there p is in U and n in U perp. And there please never forget that the only vector that these 2 subspaces have in common is the 0 vector. In fact, this is exactly why we have the uniqueness of this decomposition. And now here we can bring p to the left hand side, and then we also have 2 different subspaces left and right. Namely, we already know that we have U perp here on the right hand side, and on the other hand, on the left hand side, we have our double orthogonal complement. This is not so complicated because y is in U double perp by assumption, and for p we also know it because it's in U, and by the first inclusion we also know it lies in our double orthogonal complement. However, as already mentioned, we know that the intersection of the orthogonal complement with the original subspace is always just the 0 vector. And of course this also holds for U perp itself, and this is the result we need. It tells us that y and p are the same vector, and therefore y also lies in U. And this is exactly what we wanted to prove, and with that we are finished. And indeed this result here is quite helpful when we want to calculate with orthogonal complements in a Hilbert space. For example, it immediately allows us to see this vector n as the orthogonal projection of y onto our orthogonal complement. So maybe let's immediately write this down as a general result. So each vector x from our Hilbert space can be uniquely decomposed into 2 orthogonal projections. The first one is the one onto our closed subspace U, and the second one the one onto our closed subspace given by the orthogonal complement. Therefore this notation here with the vertical line makes sense, but please keep in mind this only holds for a closed subspace U. And under this assumption, we immediately get a well-defined linear operator we can call P with index U. And as a linear operator, it maps our Hilbert space X into itself. Hence, the input is any vector X from the Hilbert space, and the output is the orthogonal projection onto U. Hence, for any vector X, we just forget about our orthogonal component and just take the one in U. And moreover, we already know a very explicit formula for this operator when we have an O and B for our closed subspace U given. So as always, let's denote this O and B by E alpha, and then we can write Pu as a finite or infinite sum over these E alpha. In fact, you might have already seen it written in an informal way like that. And I would say this is an easy way to remember this operator because you have one-dimensional projections and you sum them up. However, the official mathematical meaning of this short notation here tells us that you have to apply Pu to a vector X. And then the image is given as a limit inside our Hilbert space X. So there you see, this is how our linear operator acts on a vector X when we have an O and B for our subspace. Indeed, we already know this from the last video, but now we will discuss this operator Pu itself. And first I should tell you that the operator itself is also called an orthogonal projection. And in the case that this is confusing, you could also say that Pu is an orthogonal projection operator. Now it's worth noting that we already know a lot of properties of this new linear operator. First of all, since we project our vector X onto a subspace U, we already know the range of our Pu. So these are all the elements we can hit with our linear map, and obviously this is the whole subspace U. Clearly it cannot be bigger than U because we project onto U, and we hit all the elements in U because we can just take any U as an input as well. So this is not so complicated, but definitely important to remember. The range of such an orthogonal projection operator is always a closed subspace. Then on the other hand, we can also say something about the kernel of Pu. These are all the elements that are sent to 0, and obviously this is the orthogonal complement of U. And then for the third property, we can look at the operator norm of Pu. And there please recall, the operator norm is the largest length we can reach in our image when we use normalized vectors. So more concretely, you take the supremum over all possible vectors X from the Hilbert space that have norm 1. And then you calculate the length of Pux. And of course, the norm here, the length, is just the induced norm in the Hilbert space. Okay, so this is the operator norm, and for our Pu, this one is almost always equal to 1. This is also quite clear, because if we project a vector, it cannot get larger in length. In fact, this is just the Pythagorean theorem in action. However, there's one exception here, namely when we project everything to the 0 vector. So in the case that U is this trivial subspace here, then the operator norm of Pu would be equal to 0. And this is the only exception, otherwise we always have the operator norm given as 1. And now the last property here is telling you what happens when we apply Pu several times. And as you might already guess, twice is as good as once. Indeed, after applying Pu once, we are already inside our closed subspace U, and projecting it again does not do anything anymore. And you might already know this property, we usually call it idempotent. Therefore now please remember, an orthogonal projection operator is always idempotent, so applying it more than once is not doing anything anymore. And now it turns out that these 4 properties already completely determine that we have an orthogonal projection here. This means any bounded linear operator P with these 4 properties has to be an orthogonal projection. And please note, if we say bounded to an operator, we mean that this operator norm here is finite. In fact, this third property here already follows, so we just have to assume the other ones. Hence what we get here is an equivalence. P is an orthogonal projection if and only if P is idempotent and the range of P is given as the orthogonal complement of the kernel. So these 2 assumptions are already enough to get an orthogonal projection. And for the end of this video, let's write down the proof of that. And there the first implication should be simple, so let's assume that P is already an orthogonal projection. This means P is actually an operator Pu for a closed subspace U. Hence, idempotent is already given by the fourth property. And moreover, we can easily combine the second and the first property to show this relation. More precisely, the second property tells us that the kernel is given by the orthogonal complement of U, and now we use the perp operator on both sides. Therefore, we can finally use what we have proven at the beginning of the video, namely that using this perp operation 2 times gives us our original U back. And by property 1, we know that U is just our range. And there we have it, this already shows the first implication. And in the next step, we will show that this is already sufficient for being an orthogonal projection. So here we just assume 2 things. First, that P squared is equal to P, and second, that the range is orthogonal to the kernel. However, this equality with the orthogonal complement already tells us that the range of P is closed. So this is a standard property of the orthogonal complement, and now we can use it to define our closed subspace U. And with respect to this U, we can just use our standard projection theorem, which means our decomposition for any vector x. And there we just have to show that if we apply P to this x, we get out our x projected to U. So let's simply do that. Let's apply P on both sides. So this is quite simple. We just have to know what happens when we put a vector from U into P. Or maybe first we should discuss what happens when we put a vector from our orthogonal complement in. Indeed, the assumption from before tells us that the orthogonal complement of U is exactly the kernel of P. So again, we use 2 times the orthogonal complement operation, and you should know that the kernel of a bounded linear operator is always closed. Therefore, this equality here is correct, and we know that we put something from the kernel in here, which means we get out the 0 vector. Therefore, we just have to talk about the first element here, but there we know it lies in the image of P. Hence, by definition, we find a pre-image such that P of this pre-image gives us our x projected to U. So maybe let's simply call this pre-image Z, and this one we can use now. So again, Z is chosen in such a way that we get x restricted to U out. However, now instead of P, we could also write P squared. We know it's idempotent, so this one does not change anything. However, we already know that P of Z gives us our vector, so only one P remains. Hence, what we actually get is that P applied to such an element from the range does not change anything. And with that we are finished now. P of x is exactly the orthogonal projection of x onto U. So our general operator P is actually an orthogonal projection operator. And this finishes our proof. Now we have a nice characterization for orthogonal projection operators. We just need an idempotent operator that satisfies this equation. And now the nice thing is that this last equation has something to do with self-adjointness of an operator. Therefore, we should definitely talk more about self-adjoint operators in the next videos. So I really hope I meet you there again, and have a nice day. Bye bye.